So if we're going to think about transition state geometries, right, so that we can think about how an enzyme could complement the transition state and therefore decrease the energy of the transition state and decrease the activation energy. And let's see what that might look like for a transition state. So let's take the example of proline racemase, which is an isomerase enzyme. Okay, and so what this does is this converts L-proline, okay, which is canonical amino acid, so to the other stereoisomer, which is D-proline. Okay, so it's just shifting the stereoconfiguration of the alpha carbon, okay, for proline. Right? So the way you can think about a transition state, so if this is just if this is the reaction and there's only one transition state in between L-proline and D-proline, then you can think about the transition state as being an average of the two, right, structurally. And so what that would look like then is that if we're looking at, for instance, the carboxylate group, right, if the carboxylate group, we have a deprotonation, then we have the carboxyl group. The carboxyl group would be in this halfway point between the L position and the D position. And so what that would look like is something like a trigonal planar carbon, alpha carbon, which we intuitively know isn't something that we would normally see for carbon. But that's why it's a transition state, right? It's high energy. It's not something we can isolate. It's not something that exists long enough that we can see it. But it's just a way for us to think about, well, okay, how could an enzyme stabilize the transition state? So it's kind of a made-up geometry that we can use to think about how enzymes work. All right. So again, this is kind of a structural average of the substrate and the product, and so we make this. We can think of it as this trigonal planar carbon with the CO minus in the middle of the two positions, and we can think of this as being our transition state for this reaction.